Perfect. Thank you for being here today. My name is Hiral Patel. I'm a Senior Principal Architect and Director of Engineering at Yahoo for the Search and Native Ads Reporting Platform.
A little closer.
Okay. I've worked on big data at various companies in the Bay, using both open source as well as closed source solutions. I'm going to be talking about query generation across multiple data stores today. So we're going to cover some of the reasons behind query generation, some of the things we did to evolve our query generation process for our use cases. We'll consider some of the open source alternatives that are out there, as well as look at some of our production results and what we're working on next. How many of you here know what we mean by OLAP queries? Awesome. Most of the room. So I'm going to not cover too much in depth here. In general, for data warehousing, the most common data model that's used is the star schema or the snowflake schema. Here we have dimensions, which are the reference information which give context to a fact. A fact is a measure, a value that represents a fact about a managed system or an entity. In the ad system world, a dimension is something like the ads that are in the system, the campaigns, or the ad groups. Those are the dimensions. A fact would be something like the number of views associated with an ad, or the number of clicks associated with that ad, or the spend associated with that ad. So those would be the facts or measures. Let's take an example cube definition. We have here a performance stats cube, which essentially consists of 3 tables at 3 different levels. We have the ad stats table, which is giving us spend across ads. The ad group table, which gives us spend across the ad group. And then the campaign stats table. So let's say if I wanted to run a query to get the spend associated with a particular campaign. The best table to run this query on is the table that's going to require me to aggregate the least number of rows to get that data, in which case we want to run that query on the campaign stats table because we're looking at campaign spend. So this cube definition has essentially a base table, which we call the ad stats table. As we define the cube, we roll up the ad stats table to the ad group stats table by discarding a single a dimension value, ad ID. So we can go from the ad stats table to ad group stats table by simply saying, OK, I'm going to discard one column, right? And then I can do the same thing with the campaign stats table by taking the ad group stats table and discard a single column called ad group ID. So this is how we build our hierarchy. I'm going to be using the terms fields and columns interchangeably. I'm going to be using data store and engine interchangeably. When I say something is a dimension-driven, I'm talking about a query where the driving table is a dimension table. And a query like that would be, give me all of my ads sorted on ad ID descending. So that would be a query where the driving table is a dimension table. A fact-driven query would be something like, give me the top 50 ads on spend descending. That would be a fact-driven query. So why query generation? Right? What's the big deal? For our primary use case, it was to make it simple for our users to query the data that they needed. A simple interface. We don't want our users to worry about figuring out what tables they needed to join with, what are the dimensions, what are the fact tables, how to construct the query, or worry about the kind of join conditions that they need to have, be it either inner join or outer join or left outer join or right outer join. So we wanted to make it so it was easy for them to query the data that they wanted by just selecting the fields that they wanted and providing a set of filters. We also wanted to make it easy to decouple our interface from the target data store where we ran the query. So we can make it we can easily transition from one data store to another without impacting our users. We also have multiple use cases. In this case, we have UI users who want to manage their entities like ads and campaigns. And those are generally dimension-driven queries. They're managing their entities, changing the ad title or whatever, but they also want to see the factual information like the impressions or the spend that they have associated with that ad. The other use case we have is users running reports, the traditional reporting use case where they say, hey, can you run this report for me? And we say, OK, sure, we'll run it asynchronously. Here's the job ID. Come back later and check to see if it's done. And once it's done, they can grab it from a location that we provide them. Right? So that's an asynchronous use case. And those are mostly fact-driven queries. We also wanted to centralize our reporting system. We didn't want to have the business logic being applied across multiple teams and having disparity in how it was being applied. Right? So we wanted a single source of truth for the reporting system. So there are many choices when selecting a data store for OLAP queries. What do you choose? Right? Is it going to be the same data store forever? Are you ever going to have to change? And the answer is going to be yes. Most likely, you're going to have to change at some point. Our solution generally evolves over time. We start simple. We use a data store that we know best, right? As the business grows or we start hitting bottlenecks, we start looking at other solutions. We may find that a certain data store is really good at a certain type of OLAP query versus another data store, and we want to use both of them, right? Instead of trying to find one data store that solves all of our problems. We may find that we have heavy investment in one technology, and we don't want to transition off of it like this. We want to have the ability to use a separate technology which may be more horizontally scalable and transition incrementally. We may also find that the cost of transition is high, right? So we don't want to migrate from one data store to another, and we may want to support both of them concurrently, right? This is where generating queries across multiple data stores makes it easy to evolve our solution over time. So when we first started, we took a simple approach by defining an interface for all the things that we're interested in for query generation and putting it in an interface. For dimension definitions, this is what the interface looked like. It was pretty trivial. And we did something similar for a fact interface. You have the fact table, name, the columns you're interested in, the group by, the predicates that you're interested in. It's a simple interface. You can easily implement it and add as many tables as you like. However, we quickly realized the challenges to this approach. As the number of cube definitions and the number of tables increased, it was difficult to scale. Our solution just wasn't generic enough. We didn't have things like derived expressions. For example, click-through rate is a derived expression based on impressions and clicks, right? We had no way of defining that. We had no way of providing hints for optimizations at query construction time, like if it's a fact-driven query, I want to use this hint. If it's a dimension-driven query, I want to use this hint. Or maybe we have a use case where we always want to provide a filter on a column, right? Regardless of what the incoming request wants, we're saying, OK, I want to force this filter on this table, regardless of what the user wants, right? So those are constraints or special casing that was not available. And so we knew we needed a different solution. So our second approach was to build a SQL-like DSL for cube definitions. This allowed us to easily add multiple definitions for cubes and evolve our feature set. Here's an example definition where we were defining the performance stats cube with the mapping of the internal columns to the external columns. And we're saying that it's based off the add stats table. We also wanted to add the ability to easily define constraints at the column level as well as at the table definition level. So we added annotations. As you can see, we have an annotation here to define foreign key constraint on dimension table for all our dimension entities. And we also have a table annotation that tells us to use the Hive engine for this definition. We also wanted to easily support, defining rollups easily. So this was accomplished by constructing a simple rollup using an existing base table. So using the same example we looked at earlier, we can construct a add group stats definition by doing a simple rollup of the add stats table by discarding the add ID. So it's something that we talked about earlier, and now it's just in DSL form. And here we can also define annotations on grain, like if the table is an hourly table or if a table is a daily table. This can be useful when we want to determine the time range of the query. Right? If the query is looking for data for the last 3 hours and they want hourly data, we'll use a table that has the hourly grain, versus if they want data across the last 7 days at the daily grain, then we will use the daily grain tables. This is another way of optimizing how we're running the query, how many rows we're going to have to aggregate across to get the data we want, right? We can also define things like Hive partitioning type. So how the tables are partitioned, we can define our partitioning schemes through annotations. So what we do when we construct the actual SQL query is inspect the definitions that we've constructed already using our DSL at the request time. So when a request comes in, we inspect these definitions, we figure out what the constraints are, we figure out what the special casing that needs to happen for the columns, and construct engine-specific SQL based on whichever table we selected to answer this request. Over time, we also found challenges with this approach. We found that we were limiting ourselves to selecting a table based solely on the columns that were available. So we couldn't make a decision on how to go from select one table, select one data store over another. There's no intelligence that says, okay, this data store is the best data store suited to answer this kind of request. It was solely based on what columns were available. We also found it difficult to extend our existing implementation beyond the 2 data stores that we supported. It was just not generic enough. There was, the DSL was great, but it was also prone to human error. We didn't have a lot of error checking and error handling at definition construction time, which led to potential issues that could be found in our functional testing environment or even in production, though it happened rarely. Also, the annotations that we also liked a lot because it allowed us to solve a lot of our special casing use cases, but they promoted arbitrary special casing. We would find that 2 annotations may end up actually doing the same exact thing. So there's some duplication of code by 2 different engineers that inserted the feature at different parts of the pipeline, but they did the same thing. So this is where we turned to Scala. We converted everything over to a Scala implementation, except for it was all statically typed DSL. We retained much of the same functionality we had in our previous version, except for we could now rely on Scala to help us find the errors in our definitions at compile time as well as construction time. So for example, here we have the last column defined here as a derived column called add status. And it is basically a decode of an existing column called status. And we reference it using curlies here. at construction time, we can basically go in there and see, does this reference column actually exist in our definition, right? So at construction time, we can validate that this definition is correct. We can also do things like take a look at the annotations that are available. And if the annotation is engine specific, I can validate that this annotation is applied to a table definition for the correct engine. So if I was, for example, using a Hive partitioning scheme for a definition for an Oracle table, then it would fail construction. It would check these things and just tell the developer, hey, you need to fix this. It doesn't get past our unit tests. We did something similar for facts. As you can see here, we have foreign key constraints defined for these columns, and we can also at construction time check to see are these table references do they actually exist in our registry of all the dimension tables. So we can do that at construction time and validate that all of these references are actually correct. We also have the same derived column at the bottom there called the Hive derived fact column for video starts. I don't know if you can see it very well. I guess you can. But it is more or less a sum of decode, which relies on two different columns. One is a dimension column, and the other is a fact column. So the result of these definitions here, for when I call the new fact method here, it is essentially defining my base table. So this is where I would define the add stats table. It returns a fact builder object, and I can use this builder object to then easily add on the rollups that we had talked about earlier, just the same way we did with the SQL-based DSL that we looked at earlier. So we retain much of the same functionality, except for it's all statically typed and easy for us to find errors at construction time and not have as many problems in our func test environments as well as our production environments. So once the definitions are constructed, we can convert the builder into a actual cube definition by calling the toPublicFact method here. What we're providing here is two sets of columns, the set of dimension columns and the set of fact columns that are available in this cube definition. So in this definition, you see the mappings of the internal columns to the external column names and a set of operations that we're allowing people, our users, to apply on these columns. We can also specify any forced filters that we want. For example, if I wanted to always force a filter on source column where the source was always equal to 2, I can specify that right here. We can also specify the maximum number of days that we want to allow a query to run on this cube. Or we can also specify the maximum days look back. For example, if my maximum days allowed on this cube was 30 days and the maximum look back was 400 days, then what I'm basically saying is I can query any 30 days spanning the last 400 days. So these kinds of constraints I can define easily at the cube definition time. So I don't have to special case anything. I don't have to modify my REST API every time I have different constraints for different cube definitions. To get to where we are now, what we did is we took all the common concepts from the data model and put them into a request model. The request model is essentially data store agnostic. It doesn't know anything about what data store is going to be answering this particular request. So we took all the common things and put them in one place and had the query generators a little less complex by allowing them to just work on this request model. So the query generators essentially take this request model and generate a query for the data store they're registered against. And similarly, the query executor is then also taking the query and generating and executing the query against the data store it is registered against. So the executor then more or less populates the result into a row list. The idea behind using a registry for the generators and executors is that we can now have multiple implementations for the query generators and executors across each data store, and which allows us to easily address multiple use cases. We can also make our query generation more intelligent by plugging in cost estimators. So I can add in a cost estimator for dimension cost. So for a given request, I can see, hey, what's the join cardinality associated with this request? And similarly for the fact, I can try to estimate the number of rows I'm going to have to aggregate for this particular request when the request comes in. We can take this information and put it into our request model and allow all the components downstream to make decisions on optimizations as they see fit using this information. Our partition columns, or our definitions are partition column aware. So if I wanted to plug in a custom partitioning scheme, I would just need to implement a trait and pass it into my query generator to render our partition columns. In order to push changes out to production, we added versioning to our cube definitions. And as a part of pushing out the new definitions, we added the ability to bucket test those definitions to various sets of users. So as we increase the bucket size and feel that the new definitions are good enough, we can essentially update the default version to be the new version of the cube definition. This allows us to easily make changes in production, test them out to a certain set of users, and make sure that there's no user impact. Let's take a quick look at how a UI request for a UI request data flow would look like. So we would have an HTTP request coming in with a JSON describing what the user wants. We would validate the object, create the request object, and use this request object to generate our request model. The request model itself is generated by inspecting the registered cube definitions and looking at the time providers. Maybe our partitioning scheme requires us to do time zone conversions. Maybe not all of our users are in the same time zone, right? So we can get that information from a pluggable time zone provider or a time provider. And we can also get the cost estimates for the tables that we're interested in. So what we do is we create a request model that has all the dimension candidates that can potentially use to answer this request, and all the fact candidate tables that can be used to answer this request, as well as attach all of the cost associated with using those tables for dimensions and facts. We can take this information now and generate a query pipeline. A query pipeline essentially is a way for us to define how we're going to run this request. In the case where this is a synchronous query, we know that this query is meant to be for the UI. So we're going to respond with a JSON response immediately, right? So the query pipeline essentially is generated to work with the use case that we're trying to solve for at query time, right? So the query pipeline is also responsible for determining what's the best data store to hit, which table to hit. All that stuff is determined by the query pipeline.
So if you can answer synchronously to every request,
Yeah.
why would you do async?
Yes. Yeah, so the question is, if I can do a synchronous request, why answer it asynchronously, right? So not all of our requests are synchronous. So if you look at the UI use case, all of the requests are paginated. You're not going to be able to look at 1 million ads at a time, right? So in the case where a user wants to run a report across all of their ads, that's going to be an asynchronous report because there's no way we're going to be returning 1 million rows for that use case. So once we have a query pipeline, we can take this query pipeline, which is more or less a program of how we're going to answer this request, and schedule it to run on a separate thread, which then essentially, once executed, produces the row list which has all the data that we need, and we convert this into a JSON output stream and complete our async response. Since we use Druid, and it doesn't support joins out of the box, one important use case for us was to be able to query across multiple data stores. In order to do this, we used our query pipeline abstraction. The query pipeline abstraction, again, is how we execute a particular request. So this is where we can make the decision on querying across multiple engines. So this is the use case where we query Oracle for the dimension data, and we query Druid for the factual data and merge the results in the API itself. So let's take an example of getting the top 50 ads with spend descending. In that example, we would query Druid to get the ad ID and the spend information. Once we have all the entity IDs, we can construct an Oracle query to get the ad title and the ad description for those entities. Once we have that data, we can merge it with the data from the first request and serve it out as a JSON output. So this is more or less a unique use case for us, where we're trying to query across multiple data stores and use each data store for what it's best at. So why not use one of the open source alternatives like Kylin or Lens? Is anyone aware of Kylin or Lens here? All right, a few people. All right. So Kylin is more or less an end-to-end product for managing your cubes. It generates the data, it manages storage, it also provides its own ANSI SQL interface. Lens is closer to what we've built, but it is still more like managing a database. It also manages your query lifecycle. It provides a kubecql interface, which is more like a HiveQL subset. For us, our primary use case was to use a library or a framework approach so we can easily integrate this into our existing components. We don't manage storage, and we don't manage the ETL that produces the data. Our query lifecycles are managed by the users of the library themselves. We just provide them the abstractions to execute the query. It's the users of the library who manage actually scheduling the query on a thread and getting the results and doing whatever they want with the results. We just provide the abstractions. And also, we wanted to provide a simple JSON interface to our customers. That was, again, our primary use case. We don't want our users to construct any form of SQL. And we wanted to easily optimize and customize our generators. So optimization for our different use cases was very important for us. Here's an example JSON input. It's pretty simple. All we have is the cube that we're interested in, the fields that we're interested in, and the filters. Here we're looking at 8 days of data for a particular advertiser. So our advertisers, which are mostly our customers, worry about a simple JSON input like this, and that gets converted into a query that's joining across 4 tables for this query, because we would have to get the campaign name, the ad group name, and the ad title. So we would join across four tables to get this data. Here's a set of optimizations that we've built using the cost estimation information that is passed down through the request model. For Druid, we have roughly 4,000. Our Druid cluster has roughly 4,000 cores that are threaded, and we can make decisions on how many cores we want to allocate to running a particular request based on the cost estimation information that is passed through. We can also make decisions on what kind of hints we want to send Oracle, depending on the kind of query it is.
Isn't the next speech should be starting?
No, this is a 14-minute.
Oh. Sorry.
All right.
Unlike this.
So for Hive and Oracle, we can also do things like predicate pushdown. So when we're joining with large dimensions, and some of our dimensions are tens of billions of rows, predicate pushdown becomes a very important optimization. So in production, we run millions of OLAP queries per day. So query optimization is not a nice to have, it's a must have in order to make sure that we have our SLAs, we are within our SLAs. We have 30 plus cube definitions across 3 data stores, Hive, Oracle, and Druid. Our Druid cluster itself is segmented on the idea of tiers of service. So we have 3 tiers of service, which is supported by our Druid cluster, and Druid is actually one of the few database or data stores which allows you to tier your storage and tier your brokers, your actual compute. Our current version of the query generator is 3 times faster than our previous version, which was all written in Java. Though I'm not saying the Java version was slow because it was written in Java. It was just the implementation. Our current implementation is 20% less code, has more features, has better validation and error handling, and this is my plug for Scala, essentially.
Question. So you talk about the query generation time. What about the query execution time? Is the query execution time about the same?
Yeah, query execution is the same. Sorry, the question was, is the query execution time any different? And the query execution time is not different because that's entirely tied to the data stores. However, because we're able to make these optimizations on things like determining the number of cores and using the right hints and sending the query to the right data store based on how costly of a query it is to run, our overall numbers for like 99% of the time the query is executed in a certain amount of time, those numbers have come down drastically because we're making more intelligent decisions on where to run the query. And
The average is going down or variance?
no, the average has gone down.
Okay.
Yeah.
The question, is it possible you do joins across different data stores? Like you want to join a table on Hive and another table on Oracle, for example?
No, we don't support joins. So we don't, the question was, do we support joins across data stores? The only place we support joins across data stores is in the UI use case. And the UI use case is a special case because all the UI results are paginated, right? So when you're taking a subset of the results and sending them through the UI, you can't afford to do API side joins. And that's what we do.
So you're joining the results return from each store, you allow this, but not allow direct join across the store.
Yes, we don't allow direct. So you can basically have dimensions that are defined in Oracle, and you have facts that are defined in Druid, and the framework itself will do the API side joins for you. You don't have to do anything, but that only works for the UI use case. Because the async use case is not run in the API side. The async use case, we have separate workers which use the same libraries to execute the actual async queries, right? So this is what I mean. We've taken a library approach so we can reuse some existing infrastructure of how we process the async use case versus the synchronous response use case.
Is it planned to add this feature across stores?
We are looking at it, yeah.
Wait, so your earlier example of joining Druid and Oracle, that is like the so-called, what you call UI use case?
Yes, that's the UI use case because all the UI results are paginated, right? So you can only show the user a certain number of rows, right? So in that use case, we can do cross data store joins on the API side. All right. So we've also integrated our REST API into an open source data visualization tool called Caravelle that's built by Airbnb, which they recently renamed to Superset. And it more or less addresses all of our internal reporting needs. So some of the work we're working on right now is to add view support, to add fact join support. We also want to take into consideration the load on the data store while we're trying to decide on which engine to select. So if one data store is at a certain percent capacity, whereas the other one is underutilized, then even though we can answer the query best with the data store that's loaded, I'd rather send it to the secondary data store because it doesn't have any load, right? So those are things that we don't currently take into consideration. We also want to take into consideration data availability. So for example, in the use case where we need to do reprocessing and loading into one data store, we want to take that into consideration. We want to make sure that our users are not hitting a data store where the data is in the process of being deleted or replaced, right? So we don't currently take that into consideration, though we do, actually I take that back, we do take that into consideration for the async use case, but not the synchronous use case. We're also considering open sourcing this library / framework. We're not sure how much interest there would be. If this is something that would be of interest to you, do let me know so I can take it to my boss. So I've shared our journey for building a general framework for query generation for OLAP queries. Of course, it would not have been possible without all the engineers on my team. Hopefully, I've given you guys some insights in how you could go about solving a similar problem that in your use cases. I can go through an actual cube definition in IntelliJ so you can see what it looks like. Okay. Go ahead.
Can you say something more about that dimension, say dimension join 2 slides again or something? Future word, yeah, add fact dimension view support, Can you say more about that?
Yeah, so the question is, can I talk more about the fact-dim view and the fact joint support work? So fact-dim view support is basically allowing us to define views inside of the table definitions itself. So in Oracle, I can create a view by doing a union across 2 tables and define a view doing that. Instead of having to define the view in Oracle, I want to be able to do that directly in my query, in my table definitions, right? So that way I don't have to worry about how that view is actually constructed. The view is more or less just a query across two tables, right? So the query generator itself should be able to generate that on its own. I should just be able to tell the definition itself that, hey, generate a view across these 2 tables. Right? So we want to add that support directly into the definitions themselves instead of having to have DDL that goes in there and updates the views in Oracle or Hive. Fact join support is our use cases where we want to get factual information across multiple facts and join it together. Right? So we don't really support fact use cases right now. Our primary use cases are fact and dim joins. All right, I got 1 minute, so I'm going to skip this. Questions? If no questions, I can go through the definitions if you'd like. Okay. So this is a definition for our keyword stats cube. Keyword stats cube is basically performance information about keywords that our customers are interested in. As you can see, it looks similar to what I talked about before. A few things that I can tell you about is that we haven't already talked about is this idea of static mappings. I can define a static mapping for fields. For example, the data for price type in the actual table is just a numeric value. But externally, I don't want to show users a numeric value. I can map it back to a human readable value, like price type of 1 is CPC, right? At the same time, this allows me to do a reverse mapping. So my customers can tell me, okay, give me, I want to add a filter where I'm only interested in where ads where or keywords where the price type is CPC, and we will do a reverse mapping as a part of the query generation process to map CPC when we're adding the filters. And another thing that we didn't talk about here is this idea of aliasing. So one thing that you'll encounter is while you're creating tables, one table may have the name for a field as device type ID, whereas another table may have the field named as device ID. So you may have problems where the naming is not consistent, right? So how do you get around that problem? And so the way that we do that is we just alias it. So with this, we have this idea that although we have a single mapping when we define our cubes for an internal field to an external field, that internal field name itself may have to be aliased depending on the actual table's schema definition, right? So we don't want to go in there and rename tables every time there's a mismatch in the fields, right? So we can change that or accommodate that at the time of query generation. Okay, I think I'm out of time. So one last thing. So here we can also define constraints around when to choose which engine, right? So we have this dimension cardinality lookup, which says, okay, if the dimension cardinality estimate is between 0 and 800, my cost multiplier for a particular engine is 1. If it's between 800 and 100,000, then I want to hit Druid if possible, essentially. So at definition time, we can make these changes and look at how the system performs based on some of these metrics and make these adjustments as time goes on. All right, thank you very much.